Yes, so hi everybody, my name is Aurore. I'm a visiting assistant professor at Stanford and a research group leader at CISPA. And so my research really focuses on web security and privacy and web measurement. And today I'm super excited to be here at RuhrSec 2022, especially in person. And I'm very happy to give you an overview of one of our most research work on browser extension security, or actually rather insecurity, which we presented at ACM CCS 2021. All right, so as you probably all know, browser extensions are popular to improve user browsing experience. For example, they can add ad blocking capabilities or just be a nice add-ons, for example, to customize browser user interface. But at the same time, browser extensions can introduce severe security and privacy threats and put the large user base at risk. For example, browser extensions can lead to the execution of arbitrary code in any websites, even without a vulnerability in the websites themselves, or sensitive user data exfiltration, again, to any websites. So that's pretty serious. How is this even possible, actually? So by design, browser extensions have access to privileged APIs and features. For example, to be effective, an ad blocker needs to modify web page content or intercept network requests. In addition, browser extensions can do tasks that web applications cannot traditionally do. For example, web applications are subject to the same origin policy, meaning that which restricts the resources that they can access, whereas browser extensions can access arbitrary cross-domain data even when a user is logged in. Here I would like to highlight that this work was conducted between 2020 and 2021, and since then Chrome released kind of new rules for the browser extension ecosystem, so this manifest version 3. So some things that I'm going to present are not necessarily true today anymore, but it depends to which rules the extensions are adhering. So yeah, my point was browser extensions are highly privileged, so they have more privileges than traditional web pages. And obviously, due to their elevated privileges, browser extensions attract the interest of attackers. So here, I would like to distinguish two categories of, things that could go wrong with extensions. So on the one hand, we have malicious browser extensions, meaning extensions designed by malicious actors with the aim of harming victims. But the good news is Google engineers are actively working on detecting malicious browser extensions in their store. For example, in 2020, they removed extensions exfiltrating user data. They removed extensions spying on users. They also removed extensions hijacking cryptocurrency wallets or extensions redirecting to phishing websites. So overall, between 2020 and 2021, they removed over 500 extensions from their store. In addition, Google also has this review system, so they review extensions prior to publication on the Chrome Web Store. And so overall, this makes it harder to have malicious browser extensions, so in the Chrome Web Store today. Unfortunately, malicious browser extension is not the only type of extensions that can lead to security or privacy issues. There are also vulnerable browser extensions. So this time, benign but buggy extensions, so designed by well-intentioned developers, but which contains some vulnerabilities. And so this type of extensions enables attackers to elevate their privileges to the capabilities of browser extensions. And due to their inherently benign intent, these extensions are really challenging to detect, and also they can pass through the review process conducted by Google. Little work has been done to detect vulnerable browser extensions. There is this work from Auckland 2019 from Sommet, UmpWeb, but the problem is, so he analyzed over 60,000 Chrome extensions, and his tool reported over 3,000 extensions as suspicious, meaning that he needed to manually review these 3,000 extensions, which took him like a month. And at the end, he found that 95% of these extensions were actually false positives. So in other words, detecting vulnerable extensions precisely and at scale is still an open problem, and this is the focus of my talk. All right, so before diving into our approach, you have to know that an extension is composed of several components. And these components have different privileges. First, the content script is injected into web application. And the content script can use standard DOM APIs to read or modify web pages actually similarly to the scripts directly loaded by web pages. Then we have background pages, so this time a highly privileged component which implements the core logic of extension and which has been replaced by service workers, so in the new version, so Manifest version 3. Then we have the web accessible resources, so browser extensions can expose WARs, so scripts to be executed on every web pages. And finally, the UI pages, which enable users to customize extension behaviors, for example, over different options, setups, or pop-ups. So as you can see on the slide, background pages, WARs, and UI pages are highly privileged, and they have access to the full extension's capabilities, whereas the less privileged content script only has access to a limited set of APIs. And then all these components can communicate together over messages. And the second thing, an extension can also communicate so outside of the extension, meaning with web pages or even with other extensions. All right, so as I was saying, extensions are highly privileged, which is super interesting for attackers. And so now in this slide, I'm going to present what an attacker could actually do with vulnerable extensions, which privileges an attacker could exploit. So we considered 4 things. First, an attacker could execute arbitrary code in the extension privilege context. So this is really bad, and like the worst case scenario is probably universal cross-site scripting, so the ability to execute arbitrary code in any websites, even without a vulnerability in the websites themselves. An attacker could also gain the capabilities of triggering arbitrary downloads, so without user consent or user notice. An attacker could perform arbitrary cross-origin requests, so bypassing the same origin policy. And the fourth category we considered is related to data exfiltration, so exfiltrating, for example, cookies or browsing history or most visited websites, which can lead to session hijacking, tracking, or fingerprinting. Still note that an extension, so the extension permissions are declared in a file, so the manifest file, so one extension do not necessarily have all the permissions you can see on the slide. I mean, it depends. And then the user can also accept or not, depending on how the permission is defined. So this is like the worst case scenario, but then, I mean, we are also checking if the extension has the corresponding privileges or not. All right, so now how can vulnerable extensions be exploited? And we considered 2 attacker scenarios. So the first one, the famous web attacker. So as I was saying, browser extensions can communicate with web pages over messages, meaning that a web page under the control of an attacker can send malicious payloads to a vulnerable extension tailored to exploit its flaws. In practice, an attacker, so web attacker, can just trick a user into visiting a malicious or a compromised web page under the control of an attacker that can communicate with the vulnerable extension the user has installed. And so this way, an attacker can elevate their privileges to the capabilities of an extension, and so as I was saying previously, gain the capabilities of executing arbitrary code or exfiltrate sensitive user data. All right, so an example of like such a vulnerable extension. So this is a very simplistic example. We only have an extension with one component, a content script. And what is going on here is the content script is just listening to messages coming from any web pages. And then the received messages is flying into eval. So here we have arbitrary code execution in the content script, which could lead to the attacker being able to exploit all the extension privileges, for example. It would actually be worse if this would be in the background page, because due to the extension elevated privileges, an attacker would have like universal cross-site scripting. So obviously having a compromised web page is already a problem, but having a compromised browser extension is actually much more powerful because a web attacker can exploit the extension elevated privileges to attack unrelated sites and exfiltrate sensitive user data to any websites. All right, second scenario then, confused deputy. So an attacker can trick a user into installing a specific extension under the control of an attacker. And so as previously, so this malicious extension would send a malicious payload to the vulnerable extension the attacker is trying to exploit. And so the vulnerable extension is actually the confused deputy. And so a malicious extension using this technique is much harder to detect than a classical malicious extension because it does not need to have like any specific permission or actually use any suspicious APIs. This extension could just pretend to do like whatever, and actually what it is doing like in the background is just sending malicious payloads to exploit vulnerable extensions. And so such extension can actually pass through the review process conducted by Google. So we just did like a small case study to evaluate the feasibility of such an attack. So we wrote a small browser extension which pretended to customize the default new tab page, but was actually sending malicious payloads to two vulnerable extensions we detected. And so we uploaded our extension on the Chrome Web Store, and after like one day, like the extension was on the store, and so we could install it along with the two vulnerable extensions we were targeting, and we can confirm that we could actually exploit these two extensions. But here again, I would like to highlight this was really a case study, so we did only test this extension against ourselves, so we did not harm any users. The visibility of our extension was unlisted so that only people with the link could see it, and obviously we did not advertise the link. And at the end we could check that this extension was downloaded only once by us like to test it. So no users were harmed and no details of the vulnerable extensions were made public here. All right, so here again a small example of a confused deputy case. We have two extensions, so you can see the confused deputy extension B, which is listening to messages coming from any browser extensions, because again it's a bit weird, but by default a browser extension can receive messages from any extension. So if you do not say I only want to receive a message from like this specific list of extensions, like everybody can just send you messages, and that's kind of bad. Yeah, because in this example, so this confused deputy, the vulnerable extension is calling the sensitive bookmarks API, and is just sending the results of like calling this function to like the extension which send a message in the first place. So here we have sensitive user data exfiltration to any browser extensions. And I mean, obviously for this example to work, the user would have to have like these two extensions installed. All right, so to sum up like our threat model, we consider two scenarios, a web attacker and a confused deputy. And our attackers can, or we consider like the sensitive APIs related to code execution, triggering downloads, cross-origin requests, and data exfiltration. And I show you the APIs we were considering like on a slide previously. And so based on what I just said, the vulnerabilities we are targeting are actually coming from the fact that external actors, so attackers, web pages, or other extensions, can send malicious payloads to a vulnerable extension, or that a vulnerable extension sends sensitive user data to like other folks. And so in our paper, we are working on detecting such suspicious external data flows in browser extensions. All right, so we detect suspicious external data flows with our tool DoubleX, which we presented at ACM CCS 2021. I will give you an overview of our approach on this slide and go into each component into more details in the next few slides. So first, what DoubleX is doing is abstracting the code of each extension component independently. Then we define what we called an extension dependence graph, an EDG. And here we are collecting messages exchanged between each extension components and also messages coming from outside of an extension for example, from web pages or another extension, meaning from an attacker in our threat model. Then we determine if there is a data flow between external actors and the sensitive APIs we considered. So in other words, we are looking for security or privacy critical APIs in browser extensions, and then we perform a data flow analysis to detect any path between an attacker and these sensitive APIs we are targeting. And finally, DoubleX reports the suspicious data flows it detected. So that's the overall picture. Now I will go through each component into more details. So you can see here the same example as before. So the content script receives messages from all web pages, and the messages are then flowing directly into eval. So we have code execution in the content script here. And so the first step, DoubleX builds the AST, so abstracts the code over the abstract syntax tree, which gives us a tree representation of the code syntactic structure. So you can see the AST here, but for legibility reasons, I will just show you everything on the code. Just know that we're actually working on the tree. All right, so DoubleX traverses the AST and keeps track of the encountered variable. And so this way, we can detect the dependency between the two event variables and add this data flow edge, which enables us to reason about data dependency. And so it's important here because we can see that the event variable in the eval call is actually attacker controllable. All right, so I'm going to slightly change the example here and add a condition. Again, by traversing the AST, DoubleX detects the if condition and determines that it always evaluates to true, so that the call to eval is always executed. So we add control flow edges in our AST to be able to reason about conditions. Now I'm going to slightly change the example again, so the call to eval, which is not written in plain text anymore. And here, DoubleX can compute the string concatenation and recognize the access of the eval function property of the window object with bracket notation. So we have what we call a pointer analysis module to be able to compute variable values so that we can recognize variables or APIs which are aliased or not directly written in plain text, like on the slide here. And these 4 steps that I presented are done statically. All right, so I presented our approach to abstract the source code of each extension component independently. And now I can move on to the next step and explain how we model the message interactions within and outside of an extension. I'm considering the same example as before. And so DoubleX is going to traverse the AST, so enhance with control flow information, data flow information, and pointer analysis of each extension component independently. And so by doing so, it can detect the message passing APIs to window.addEventListener, and again could recognize APIs not directly written in plain text. And once we know where the message API is, we can extract the corresponding message, which is event here. And so event is coming from a web page, meaning from an attacker in our scenario. Cool. Let's consider another example for the internal message case. So we have an extension with 2 components this time, obviously. The content script is sending a message to the background page, and the background page is receiving a message from the content script. And so by traversing the AST of each extension component independently, so we detect the message passing APIs, and then we can collect the corresponding messages. And so what we do here is that we connect the sender nodes to the corresponding receiver nodes. So we join the individual component graph with a message flow to represent message interactions. And so we built what we call this EDG, this extension dependence graph, which models message interactions within and outside of an extension. All right, and so with this EDG code abstraction, we can actually detect suspicious data flows at extension level. So the question we are trying to answer is there a data flow between external actors, so attackers, and security or privacy critical APIs in browser extensions? So our sensitive API here is eval. We have a list of sensitive APIs depending on the extension permission, as I presented you at the beginning of this presentation. And so here we have attacker controllable data, which we can track across the extension. So here, obviously, in this super simplistic example, an attacker can control the parameter of eval, so we have arbitrary code execution in the content script. And then DoubleX summarizes its findings in a data flow report. So you can see an extract of our data flow report at the bottom of the slide, where the suspicious call to eval with attacker controllable data is reported. Now I'm going to slightly change the example just so that you see that DoubleX is not always saying this is vulnerable. So I'm redefining the event variable. And as you can see, DoubleX detects a new definition. You can see the data flow between line 7 and line 8. And as you can see on the report, DoubleX correctly computes the value 42, so for like the second call to eval. So the second call to eval is not attacker controllable. So in this example, I showed you that our combination of data flow analysis and pointer analysis enables us to accurately label the first call to eval as vulnerable without misclassifying the second one. Okay, and so before you think it's only working on like small and simplistic example, I'm just considering an extension which is a bit more complicated with 2 components this time. And so what is going on? So we have a content script which again receives messages from all web pages, so from an attacker. And then the message is just stored into these 2 variables here. And the content script sends or kind of forwards the attacker controllable data to the background page. The background page receives this attacker controllable data, so which you can see with the message flow. And then this attacker controllable data is flowing into tabs.execute script. So here we have like a universal cross-site scripting in the background page. So an attacker can just execute arbitrary code in the background page, can execute arbitrary code in any websites, independently of whether the websites have vulnerabilities or not. And here, so is DoubleX report. So you can see like the vulnerable call to tabs.execute script, which is reported. So again, it's also kind of a small and simplistic example, but which illustrates the main idea of our approach. But you can know, I mean, we can also handle cases where messages are forwarded back and forth between the extension components. We can handle cases like this one, but also when attacker controllable data is exfiltrated. So it's, I mean, like the idea is the same, just we are tracking sensitive user data and seeing if the data is sent to like another extension or to web pages at some point. All right, so let's move on to the evaluation part of our approach. So we evaluated DoubleX on over 155,000 Chrome extensions, which we collected in 2021. DoubleX reported 278 extensions as having a data flow between an attacker and security or privacy critical APIs. These suspicious data flows expand to 309, these suspicious extensions, expand to 309 suspicious data flows, the majority of which are related to code execution, as you can see on the table. And so you may be wondering why we have more suspicious data flows than suspicious extensions. It's because one suspicious extension can have several suspicious data flows. I mean, it can be exploited, like several APIs of one given extension can be exploited. So we manually reviewed these 309 reports. So basically we had kind of 2 scenarios. Either they were trivially bypassable, so it was clearly vulnerable or clearly not vulnerable, and then we could label the reports accordingly, or it was a bit more complicated, and in this case we installed the extension locally and built a payload and tested whether we could exploit the extension or not. So overall, we confirmed that 89% of the suspicious data flows we've reported are indeed dangerous, meaning controllable by an attacker or are exfiltrating sensitive user data. Of those, we could exploit 209 suspicious data flows under our threat model. And again, we may be wondering why there is a difference between verified dangerous data flows and exploitable data flows. So let's take an example. If you have like a cross-origin request where an attacker can only control a part of a URL, so we have like a suspicious data flow. We have a verified dangerous data flow here, but in our threat model, we aim at making arbitrary requests, which is like not the case if an attacker can only control a part of the URL. So this would not be exploitable in our setting. All right, so now let's have a look at 4 case studies of vulnerable extensions that we found on the Chrome Web Store, so in 2021, that DoubleX detected. First extension has a total of 4,000 users and can be exploited by any websites to execute arbitrary code in the extension privilege context. So what is going on here? The content script can receive messages from any websites and then directly forwards all messages directly to the background page, so no sanitization or check, whatever. And the messages are also directly flying into a tabs.execute script. So here it's like a textbook case of universal cross-site scripting. And so obviously this example highlights the dangers of trusting input data which can be provided by like an attacker. Second example, an extension with over 200,000 users, but which can receive messages only from one specific website. But by sending messages, this website can make arbitrary requests and leak their content. So you may be wondering, I mean, perhaps the extension and the website are working together. So perhaps this is an intending functionality. I mean, it's probably the case. But the problem is, if this website gets compromised, and it does not seem so far-fetched. I mean, even Google had an XSS vulnerability in 2019. So if this website gets compromised, an attacker could leverage the extension elevated privileges to make arbitrary requests to any websites and leak their content. So this example highlights the dangers of authorizing websites to make arbitrary cross-origin requests instead of preferring the more secure coarse alternative, for example, which would restrict the resources that can be accessed. Third example we detected, so an extension with over 700,000 users, which again can communicate with only one specific website, but as previously this gets problematic if the website gets compromised. And so here what is going on, so an attacker has to send a payload to the content script, and sending a message to the content script triggers like the sending of a message to the background page asking for top site information, so for the user most consulted websites. And then this information is sent to the content script, which then forwards it to like a website, so to an attacker. So here, again, I'm highlighting the fact that having a cross-site scripting vulnerability in one website can be abused to exploit the privileges of a browser extension to access sensitive user data and exfiltrate that to like any get access to sensitive user data coming from other and unrelated websites. All right, and so last example, this extension with over 10,000 users, which registers an external message handler but does not specify the list of APIs, the list of extensions with which it can communicate. And so as I was saying at the beginning of this presentation, by default, an extension can accept messages from all extensions. And so here, the messages are ending in the URL property of the downloads.download API, and so an attacker can just download arbitrary files. All right, so here again, this example highlights the dangers of implicitly allowing the communication with all browser extensions in externally connectable message handler. All right, so if I go back to our large-scale analysis results, overall, we could exploit 184 extensions under our threat model, 172 are over a web attacker, and 12 are exploitable through an unprivileged extension. Of those vulnerable extensions, 40% can be exploited by any websites or extensions. And overall, the vulnerable extensions we detected impact between 2.4 and 2.9 billion users. And finally, to evaluate the false negatives, so vulnerable extensions we may have missed, we evaluated double-cross on the vulnerable extension set released by SOME, so the work I presented at the beginning of this presentation. And so overall, we could detect 93% of known vulnerabilities. So in other words, double-cross is both very precise in terms of dangerous data flows detected and also detects most of the known vulnerabilities. Next, we conducted a similar study on Chrome extensions from 2020. Similarly, we detected 193 vulnerable extensions, so after manual analysis, and we have a precision of 90% regarding verified dangerous data flows. So again, it's very similar to the results from 2021. We disclosed our findings for extensions which could be exploited by any websites or extensions. And so we conducted like 2 disclosures, a first one in 2020 and a second one in 2021. And so overall, we reported 48 vulnerable extensions, so either to the developers or to Chrome if we could not find any developer information. And so our analysis on the Chrome Web Store in 2020 and 2021 actually enables us to reason about the life cycle of vulnerable extensions. And so what we found is, I think, a bit scary. So like of the vulnerable extensions, so in 2020, 30 are not in the store in 2021 anymore. So yeah, okay, we cannot do anything here. But only 3 extensions out of like 193 actually fixed the vulnerability we detected. 5 extensions turned vulnerable, so we had 5 extensions on the web store in 2020 which were not vulnerable, and they turned vulnerable in 2021, mostly due to permission changes. And finally, we have 19 extensions which were not in the web store in 2020 and appeared in 2021 and are vulnerable. So if you do the math, we can see that 87% of the extensions that were vulnerable in 2020 are still in the store and still vulnerable in 2021. Despite the fact that we disclosed like a part of the vulnerabilities we detected, and also half of these extensions have even been updated between 2020 and 2021, so it doesn't look so good. So we kind of assume that browser extension developers do not really have any incentives, probably to patch the vulnerabilities. Which is actually why we think that a system like DoubleX could be useful to prevent vulnerable extensions from entering the store in the first place, all the more as when they are in the store, they tend to stay in the store. Also, we believe that DoubleX could be integrated into the vetting process conducted by Google, which currently targets, as I said, malicious browser extensions. So regarding the practical applicability of our approach, so as you can see on the slide, DoubleX is pretty fast. So we can analyze 93% of the extensions. So when we consider content script and background page in less than 20 seconds. So 93% of our data set, in less than 20 seconds. And on average, we need like around 10 seconds for content script and background page, and a median time of 2.5 seconds. So in general, it's like super fast, only a couple of seconds per extension, which I think highlights also the practical applicability of our approach. So for an accurate analysis and at scale, obviously. All right, and so finally, we envision several possibilities to mitigate the vulnerabilities that we reported. So I think first and foremost, it's really important to know that the fact that browser extensions can communicate with web pages or with other extensions can lead to vulnerability, and so this should be like treated as untrusted data. And again, obviously, we cannot ban the communication between extensions and web pages or like between extensions, but we could also limit the impact of the vulnerabilities if we only allow the communication with like specified websites or specified extensions, so instead of allowing the communication with everybody by default. Also, to limit code execution, so developers could sanitize messages, so before like calling eval and friends, and they really need these APIs, but we did not really see any sanitization function when we detected such code execution things. Or even better would actually be to only execute data coming from the extension package, and so not data coming from outside of the extension, which is also what Chrome now implemented, so with the manifest version 3. And so similarly for same origin policy bypass, so like we also encourage developer, when they can and when it makes sense, to prefer the more secure CORS alternative if they don't need to access like really arbitrary cross-domain data. Then I mentioned previously that DoubleX could be integrated into the vetting process conducted by Google, but we also envisioned that developers could leverage DoubleX to also get an indication regarding potentially vulnerable data flows, so regarding critical APIs which could be exploited by attackers. And it would also be a way to increase developers' awareness regarding bad programming practices, which can unfortunately lead to security or privacy issues. And so finally, as I said at the beginning of this presentation, Chrome released new rules for the browser extension ecosystem, so this manifest version 3 in January 2021. And so migrating extensions to this manifest version would also kind of protect the user base from some of the attacks I presented previously. All right, so what should you take away from this talk? So I guess what you already know, so browser extensions are cool and useful and popular, but at the same time, they may also introduce severe security and privacy threats. I briefly mentioned the case of malicious browser extensions, but the focus of this talk was on vulnerable extensions, so benign but buggy extensions developed by well-intentioned developers. And so why extensions are interesting to attackers? Well, because they are highly privileged, more privileged than traditional web pages. And how can attackers abuse vulnerable extensions? Well, by leveraging the communication channels of extension with web pages or with other extensions. I presented our system DoubleX to detect security and privacy threats in benign but buggy browser extensions. We analyzed over 155,000 Chrome extensions and detected 184 vulnerable extensions which are exploitable under our threat model. 87% of these extensions were also already vulnerable 1 year ago. And finally, we highlighted the high precision and recall of our system. To raise awareness and enable developers to detect such security and privacy threats before large-scale deployment, we made DoubleX publicly available. And with that, I thank you very much for your attention, and I'm looking forward to your questions.